today's video is going to be the first part of many videos that will be about making a Maxwell-Boltzmann simulation. And what it means by a Maxwell-Boltzmann simulation is that I'm gonna make a simulation of a first of all, I'm gonna make an environment where there are many particles in a two-dimensional space, and those particles will be continuously colliding with the wall and between each other. And basically, what I'm gonna get is the distribution of the kinetic energy of particles in the shape that Maxwell and Boltzmann hypothesized, which is roughly this kind of shape. So yeah, that the goal is, so basically I'm gonna, by the end of making the simulation, I'm gonna have kinetic energies and frequency of particles, and basically I'm gonna have a graph that looks like something like that, and so on. Like it's gonna be about, I don't know, like 100 particles or so, maybe more. I don't know at this point, but basically I'm gonna get, the aim of my of making the simulation is yielding some kind of graph that looks similar to what Maxwell and Boltzmann hypothesized. So the first part of making the simulation is the theory. So what actually happens when two particles collide? So in the theoretical environment that Maxwell and Boltzmann, in the theoretical environment that I am going to have to make in the simulation, there's going to be two types of collisions. One being the particle colliding with the wall, and that would be fairly easy because I'm just going to assume that what happens to the particle is that when a particle collides with the wall, it basically bounces off, reflects off the wall in the same angle as the incident angle. So the reflecting angle would be same as the incident angle. That's how I'm gonna assume. But when it comes down to collision between particles, it's much more complicated. So that is the aim of today's video, to establish what happens when two particles collide with each other. So I am gonna have two particles with different mass. So there's gonna be, let's say, because also I'm gonna have to visualize what happens. So basically in the simulation, there's gonna be like a box with lots of dots, like small circles, like they're all gonna be moving, and right next to it is gonna be our graph that is gonna be plotted live to what's happening in the visual simulation. And so I'm gonna I've got two aims for making the simulation. One aim being visualizing what happens in the box, and the second one being plotting the graph. So for both, I'm gonna need to see and calculate how the momentum, how the velocity of these objects change. So collision between particles. Basically, collision means two objects being so close to each other that they exert some kind of force, an electrostatic force, such that it repels each other. So two particles getting close, repel, bounces off. That's the essence of what happens. But it's obviously more, when it comes down to calculations, it's more complicated than what it sounds. So that's what I'm going to do today. So let's say that there are two, let's say, spherical particles. All particles are assumed to be spherical, as is in the ideal gas assumption. So we have two, let's say, spheres that are in contact with each other, and there's going to be this axis, which is the axis that is tangential to both spherical circles. And what we're going to have is, so first of all, I'm going to assume that particles can have different mass. And so let's say that this particle has a mass of m, and this particle would have a mass of n. And then what I'm going to need, well, we assume that, we don't assume, like both particles we know must have some kind of velocity before collision. So let's say this particle has a velocity in this direction of magnitude v, and this particle has a velocity in, say, this direction with a magnitude u. And what we know is that some kind of force, I'm going to depict force with a different color. So I'm going to use pink for that. We know that some kind of force is exerted to both spheres, and that force would be same in magnitude. So let's say some kind of force, and this force is going to be perpendicular to this axis. So when I draw that line, it's going to be perpendicular, and that force of called F is going to be equal. And I'm not really interested in what the quantity for F is. What I'm actually interested in is what happens to the velocities of these particles, because that's what's important when I'm going to have to calculate the velocity, the final velocity, or the velocity after the collision, and also calculating the kinetic energies of the particles after the collision, of each particle after the collisions. And so there's a force of F induced in both objects, and because we know that the quantity of F is same, and also we know that the time for which the particles collide with each other is also the same. We know that the change in the momentum that occurs in both objects is going to be same. And so what we know is, first of all, I'm just going to erase F for now. And what we know about these two particles is that their final velocities are going to look something like this. So maybe this one here is going to look something like that, and that one here is going to look something like that. And what I've done here is that I'm going to say that this here is going to be the change in velocity, so change in u, the change in velocity of the mass, this mass, and that here is going to be the change in velocity of this mass. And because we said that the change in the momentum that occurs in both objects is going to be same, that's basically what the conservation of energy says, which stems from Newton's third law, that both the force experienced by both objects are in opposite directions but the same in magnitude. We could say that, first of all, m delta v is equal to n delta u. So the momentum change occurring in this object and that object is the same. And here is going to be the new velocity, which is v prime, and that here is going to be the new velocity of that one, which is u prime. Now, so how do we calculate? So our aim here is to obtain some kind of expression that gives delta v and delta u. All we know for now is that m delta v equals n delta u. So whatever we find first, maybe delta v, delta u, we must find those delta v, either delta v or delta u, in terms of what we know about the state of the particle before the collision. But because velocities are all we know about velocity for now is that the velocity of this object has a magnitude of v, velocity of this object has a magnitude of u. All we know for now is that. But what we also know about these particles is that they have some kind of, velocity is first of all a vector quantity. So first of all, these velocities are going to be they can be considered to have two components, and I'm going to say that here is theta, which we can know from, which we know. Theta, we know everything. I'm assuming that we know everything about the initial state of the condition of the particles. So I'm going to say that theta is a known constant. And also what we know, same goes for this object here. We know that we know this angle, which is going to be in that direction, and that's going to be, say, phi. And now what we want to know, well, if that is theta and that is phi, we could say that when we draw this one also here, we could say that here is theta prime and that here is phi prime. The angle, and we are also always talking about angles to the anti-clockwise direction from the vertical axis from point 0, because that's how we consider angles. When you look at the unit circle, it starts with that and then it goes counterclockwise. So that's how I'm going to define the angle. But for now, we know nothing about these final velocities. So these final velocities are also going to be helpful in establishing all of our values for delta V and delta U. So now, what could we do? We could use, first of all, we could use the law of conservation of momentum. And what we know is that before I move on, we already used conservation of momentum, so that's not the one I'm looking for. The one I'm looking for is obtaining an expression for V prime in terms of V and theta and theta prime for now. And one thing we have to know, or one thing we also know about this system is that we know the coordinates of these 2 points. And that's going to be important because when you see this system here, when I know the coordinates of these 2 points, and I somehow obtain an expression for the angle between these 2 points, we know that angle is going to be equal to this angle. So when I find this angle, so I have too many angles now, when I obtain an expression for this angle, and I'm going to call that alpha, that here is also going to be alpha. And I could also say that with this here, that is alpha, so that is going to be pi plus alpha, so 180 degrees plus alpha, because when you look at that, that's a z shape, so that angle, this angle is equal to this angle, so this angle from the horizontal 0 degree is pi, so alpha plus 180 degrees, which is pi plus alpha degrees. Pi plus alpha radians, radians. We're considering everything as radians. So that's what we know, and so we are assuming that we know everything about the initial state of the system. So I can say I do know the coordinate of these 2 points. So this point here, I'm going to say is x1 comma y1, and that point here I'm going to say is x2 comma y2, and these are known constants. So basically in the simulation that I'm going to be building, I know all of these things. I know all these constants, and these constants are m, n, u, v, x1, x2, y1, and y2. And delta v and delta u, v prime and v, u prime, theta prime, and phi prime, those are the things that I don't know. And those are the things that I'm going to have to find. But ultimately, all I'm going to have to find is delta v and delta u. So now, looking at what we have, first of all, I'm going to focus on this shape over here. So if I draw that shape again, I'm going to have, that's going to be v prime, that's going to be v, that's going to be delta v, and I'm going to have that's going to be alpha, that's going to be theta, and that's going to be theta prime. For clear our demonstration, I'm going to divide like that. So here I have 2 equations. The first one is that, first of all, I'm going to look at the horizontal plane. So I know that v prime cosine of theta prime, which is that here, this here, that's equal to v of cosine theta. So v cosine theta prime is that one here. So it's equal to v cosine theta minus delta v cosine alpha, but not minus because alpha is a obtuse angle, so it's actually going to be a plus delta v cosine alpha, but v cosine alpha is going to be a negative value, so I'm going to have plus delta v cosine of alpha. That's what I know now. And back to before I do that, back to this diagram over here. I actually have an expression for alpha, and I know that because I have alpha here and x1, y1, x2, and y2. So basically, I know that here is going to be y2 minus y1 minus y2, and that here is going to be x1 minus x2. I'm always using 1 before, so y1 minus y2, x1 minus x2, because again, alpha is an obtuse angle, so we're going to have to be, I'm going to have to define them as it is rather than looking at this is a positive value, negative value, because alpha can be, it could also be an acute angle, obtuse angle, whatever, depending on the situation. And anyways, what we have is tangent alpha is equal to y1 minus y2 over x1 minus x2, looking at this triangle over here. So we have alpha is equal to arctangent of y1 minus y2 over x1 minus x2. That's what we know about alpha, but because I don't want to write this over and over again, I'm just going to leave it as it is for now, as alpha. So basically alpha is a constant. Alpha is not a variable, alpha is a constant. That we do know. And for now I have that. I can't do anything more from this point, but we also have the vertical plane, and that's going to have the same relationship. V prime sine theta prime is equal to V sine theta plus delta V sine of alpha. Looking at, well, that here is going to be that plus that. So again, same thing. And now what we could do is square both sides and add them up. And that's going to give us V prime squared. So cosine squared theta prime plus sine squared theta prime. And I'm, of course, intentionally doing this because I know that that is equal to 1. But for now, I'm just going to leave it like that and say, again, V squared cosine, V squared cosine squared, V squared sine squared. So I can, again, wrap that up like that. And again, 1, 1. And also we know that when I square that, I'm going to have 2V delta V cosine theta cosine alpha plus square that, I'm going to have 2V delta V sine theta sine alpha plus delta V squared. So that squared, and again sine squared cosine squared repeats in both terms as alpha. And again, we all know that cosine squared or something, sine squared something, when you add them up is equal to 0. And so we could say that V prime squared is equal to V squared. So that's 1, that's 1, that's 1. So V squared plus delta V squared, so that one and that one, plus 2V delta V repeats in both expressions. So 2V delta V of cosine theta cosine alpha plus sine theta sine alpha. And what we know about let's say cosine A cosine B plus sine A sine B is that this is equal to cosine of A minus B, because we all know that cosine of something plus something is cosine something minus sine something, but we have a plus here, so we need cosine A cosine of minus B, which is cosine B. So cosine A cosine B plus minus cosine A sine of minus B, and sine of minus B we all know is minus sine B. So we have cosine A cosine B minus sine A sine B plus sine A sine B, because the minus sign is reversed. And so we have this relationship between A and B, and that's the same thing we see over here. It's A and B is substituted by theta and alpha. So we have is equal to V squared plus delta V squared plus 2V delta V of cosine theta minus alpha, like that. That's our expression for V prime squared. And yes, we have V prime squared. So now what we need is do the same thing for the bottom one over here. So now looking at the bottom diagram that we have for this one, it's quite hard to see now, but remember when I was drawing, like remember the definition of these angles when you rewind the video to when I was drawing these. So we're gonna have, using a different color for diagrams, we have the horizontal axis, we have the original u, the new u prime, so u prime, we have delta u, it's a bit different, but like that, like the direction doesn't really matter, like it could be anything, but for now, it's gonna leave it like that. And yeah, u, delta u, u prime, we know that this angle was phi, and that the bigger angle was phi prime because that's a new angle, and we knew that when we have this here, that is pi, that is alpha, so that's altogether is pi plus alpha. That's I forgot the name of those kind of angles. Angles with bigger than 180. Anyways, it's pi plus alpha. In this situation, we have an angle bigger than 180. It doesn't really matter. And we have the almost same expression, like basically same, but it's a bit different. So what we have is we have u prime. So again, looking at the horizontal components, we have u prime cosine phi prime is equal to u cosine phi plus delta u of cosine again, we're always adding, but pi plus alpha. And what we know about cosine of pi plus something is that when we look at cosine of pi plus alpha, that's going to be equal to cosine pi cosine alpha minus sine pi sine alpha. And the thing about cosine pi is that when you look at the shape of the cosine, we have cosine pi is -1, so that's going to be -1. We know that sine pi, again looking at the graph, we know that sine pi is equal to 0. So all of that is cancelled out. So what we have is minus cosine of alpha. So cosine of pi plus alpha is minus cosine alpha. So keeping that in mind, so what we know here is that it's going to be equal to minus delta u cosine of alpha, minus delta u cosine alpha. And again, when we look at the vertical direction, we have u prime of sine phi prime is equal to u sine phi plus delta u of sine of pi plus alpha. And again, sine of pi plus alpha, it yields the same kind of thing. We have sine pi cosine alpha plus cosine pi sine alpha. What we know about sine pi is equal to 0. What we know about cosine pi is equal to -1. So is equal to minus sine of alpha. So what we have is minus delta u sine of just alpha. So what we have is basically the same thing. So we're going to do the basically same thing. We are going to square both sides, both equations. So we have u prime sine squared cosine squared. So we have u prime squared is equal to, now we don't need this anymore, erase it. What we have is u prime squared is equal to, again, so that squared add it, u squared, because sine squared cosine squared add is 1. Again, delta u squared, same thing. But the only difference is going to be that the plus sign that we have here is going to be a negative sign, because when we square this side, we have minus 2u delta u, here minus 2u delta u, so minus 2u delta u is repeated in both sides, and we're going to have the sine alpha cosine alpha thing repeated once more. And so we are going to have everything equal, but the last line is going to be a negative. So we have minus 2u delta u of cosine of phi minus alpha. Again, we know that this thing is going to be repeated, but only the minus sign will change. So we have u prime squared, we have v prime squared. So now what could we apply? We already applied the concept of conservation of momentum. So only thing we have left is the principle of conservation of energy. So conservation of energy basically states that what we have, well, first of all, I'm going to assume that this collision is perfectly elastic. In the real world, collision between particles is not going to be perfectly elastic, but it's going to be very close to elastic. In fact, it's going to be one of the things that is most close to elastic, because these particles, they're so small that other forces like heat or friction that causes extra work or extra transfer of energy to something other than kinetic energy is minimized. So we could assume that the collision is almost elastical, like not completely elastic, but almost elastic. So we know that kinetic energy before the collision, which is 1/2 mv squared plus 1/2 mu squared nu squared. Don't forget that that has a mass of n and an initial velocity of u, and that's going to be equal to 1/2 mv prime squared plus 1/2 nu prime squared. We could get rid of the 1/2s and look at what I think is most convenient in this kind of thing is always look at what's repeated. So we have m repeated here. So that side we have m of v squared minus v prime squared is equal to n of u prime squared minus u squared. So before I do more, I'm just gonna leave what's important. So what we have is I want to leave the diagrams because it's always, I'm gonna reference the diagram always. I'm gonna erase all that because that's done. So that's v prime squared. So v prime squared, and all of that we also don't need. So u prime squared is all we need. Let's write that here for more space. Yeah, don't need that. So what we had is m of v squared minus v prime squared is equal to n of u prime squared minus u squared. Now, inputting what we know into these equations, we have, first of all, v squared minus v prime squared. We have v prime squared stat, so v squared minus v prime squared, we know that, well, v squared is going to be cancelled out because it's v squared minus all that, so v squared cancels out. And what we basically have is minus that. So what we have is minus of everything we have in these terms, and v squared is out. So we have n times minus delta v squared minus 2v delta v cosine of theta minus alpha. That's equal to n times u prime squared minus u squared. So what we have is everything else except u squared. So we have delta u squared minus 2u delta u cosine of theta minus alpha. And then I could expand all of it. So we have this side, I'm going to write that everything to this side because these terms are all negative, so it's going to be more convenient. We have n delta u squared minus 2n delta u, 2n u delta u cosine of theta minus alpha is equal to plus, so that's go to this side now, n delta v squared plus, so minus becomes a plus, we have 2 nv delta v cosine of theta minus alpha. Okay, now what we are going to have to use is this relationship over here, which is yielded by the conservation of momentum. We have m delta v is equal to n delta u. So I'm going to say that because m and v are more, let's say, traditional representations of mass and velocity, and I want to leave m and delta v. So it really doesn't matter what I do, but like anyways, I'm going to have, after I get delta v, I'm going to substitute everything back to delta u because what I need ultimately is expressions for both delta v and delta u. So looking at delta v first, I'm going to replace everything that contains n delta u with m delta v. So this is n delta u squared, which is going to mean that this is equal to m delta v times delta u. So m delta v delta u minus 2n. So here again we have n delta u, which is m delta v. So minus 2 u m delta v, because that is m delta v, we have u here, so u m delta v of cosine of theta minus alpha, plus this only contains what we need. And then that's equal to 0. This is also equal to 0. What we have got to do now is look at, well, we could say that all of these terms cancel out. So every single term now contains m delta v. So what we could do is eliminate m delta v from all equations. So from that would give us only delta v, 1 delta v. Again, m delta v, only have v here. So what we have is delta u minus 2u cosine of theta minus alpha plus delta v plus 2v cosine of theta minus alpha is equal to 0. And then now it's easy because we only have delta u and u, and what we know from this equation is that delta u dividing n from both sides is equal to m over n delta v, and yeah, u we know is, so u can be here because u is only a constant, so we have m over n delta v. Writing this first, so m over n delta v, that's equal to m over n delta v here, plus delta v minus, so doing plus first, plus 2v cosine of theta minus alpha. Wait, when did everything become theta and alpha? What we also need is phi. So wait, yeah, that shouldn't be a theta, that should be a phi. So that should also, wait, that should also be a phi. And then that was m delta v. Wait. Yep, that should also be a phi. And so that should also be a phi. And so that is a theta. Yeah, that is a phi. You should always be aware that phi and theta are two different things. This is theta, this is phi, they're different things. And so what we have is basically delta v times 1 plus, well, first of all, I'm going to say that, yeah, I could wrap this here by 1. So 1 plus m over n times delta v is equal to 2u of cosine of phi minus alpha minus 2v of cosine of theta minus alpha. And thus we could get our expression for the delta v, which is 2u cosine of phi minus alpha minus 2u 2v cosine of theta minus alpha over 1 plus m over n, which is m plus n over n. And so, erasing all that again, what we have is basically multiplying n to both sides. This pen is done. What we have is, so multiplying n to both sides, we have 2 nu cosine of phi minus alpha. So delta v is equal to that minus 2 nv cosine of theta minus alpha over m plus n. Or we could say it's equal to 2n over n plus n times u cosine of phi minus alpha minus v cosine of theta minus alpha. So that's our expression for delta v. And then what we could do is say, well, delta V, we know that, well, delta U is equal to, from this equation over here, m over n times delta V. So m over n delta V, oh, it's here too. So here, what we have is that times m over n. So when we look at that here, m over n times 2n over n plus n, we know that that's equal to n erased, so 2m over n plus n. So basically, this 2n over n plus n is changed by 2m over n plus n. And so what we have is 2m over n plus n, and everything else is basically the same. And then, we're not done yet, because we don't know alpha, but what we do know about alpha is that it's equal to, oh, it's all erased. Alpha is equal to arctangent of y1 minus y2 over x1 minus x2. Because alpha, basically we must calculate alpha from the coordinates of these two spheres. So our final expression for delta V is going to be equal to 2n over n plus n times u cosine of phi minus arctangent of y1 minus y2 over x1 minus x2 minus v cosine of theta minus arctangent. No, I'm not satisfied. I want to do everything in one line. So delta V is equal to 2n over n plus n times u cosine of phi minus arctangent of y1 minus y2 over x1 minus x2 cosine closed minus v cosine of theta minus arctangent of y1 minus y2 over x1 minus x2 bracket closed. And then the same thing goes for delta u, but everything now is changed by 2m over n plus n rather than 2n, and everything else is basically the same. Bracket closed, minus v cosine of theta minus arctangent y1 minus y2 over x1 minus x2, bracket closed, bracket closed. That is ultimately our expressions for delta v and delta u. Now in the next video, I'm going to have a go at making the simulation itself. I'm going to use these two equations, and what we know from these two equations is what we also know is v prime squared and v prime squared and v squared, because we see that v prime squared and u prime squared contains delta v. So when we know delta v and delta u, we know everything about the system, what happens after the collision. So thank you for watching the video. Please press the like button if you can, and subscribe. I'd be looking forward for the next video. Thank you.